Thank you. So let's move on to some predictions. So we talked about stars a bit, stellar evolution, and I'll talk a bit more about binary evolution today. But let me tell you what are the predictions from stellar evolution in terms of LIGO Virgo observations. And as you know, we have double black holes, and I will start with double black holes, but I would like to finish with a double neutron star merger and see what the implications are. And I don't want to focus on all those, nice things. We can feed that, we can feed this. I will mention what we can feed, but I would like to focus on issues because I think that's more interesting. Probably it will be up to you guys to solve those issues. I don't think the LIGO will be able to actually give us definite answers to all of the questions that I will pose. But I may be proven wrong. We'll see. A lot of people are much more optimistic, especially in the LIGO community. I think some of those issues are much more complicated and have a lot of caveats that people tend to overlook. So I would like to expose those today for you, okay? By the way, I was told, and it was totally correct, I speak too fast, and I know that. I just get excited about those things, and I forget after 5 minutes. So just, there is a sign, speak slower. Just if I go too fast, that's good. No, do show that to me. Actually, when I go too fast or something is, not clear, stop me. I can stop on one slide and finish the lecture on one slide. I talk a lot, So I have only 10 slides or 15 slides. But stop me anywhere you think it's confusing, because those are results. So I want you to understand them, okay? Just feel free to stop me. So let me start with the first, I would say, astrophysical implication of LIGO detection. So that was outbreak, really, and like epidemic outbreak of double black hole models. Now everybody can make double black holes, can make them with nice rates and nice properties, starting even from non-astrophysical sources like primordial black holes. Okay, but we will concentrate here on astrophysical sources, which are black holes made by stars. So just to give you, I'm sure Ilya has done that, but let me just give you a list, my biased list of the models. It's not fully comprehensive, but major models are included here. So first class of models is from binary stars, population 2 and population 1. So kind of no-day stars and kind of stars in a mid-evolution of universe, but already all of them include metals, so they have some stellar winds. So and I would consider that those binaries evolve in isolation, like in galactic fields. So they don't interact, or they don't interact strongly with other stars. And when you look at the mass that is included in stars in universe, that's about 90% of mass in cosmos that LIGO can see. Okay. Second most prolific channel is a dynamical channel that involves evolution in global clusters. So stars do all the dynamic interactions, and they can also form double compact objects. And that has the channels are more efficient. I will come back to this in the next line. But by mass, there is much less stars in those global clusters, about 0.1%. If you think that they may lose mass during the evolution, they do, and this is actually taken into account in this number already. Maximum you can go up, you can possibly come up to 1% here, not more than that, okay? That's what people think when they think about evolution of global clusters. Yes, that's what I'm said. I will say that in the next line. So that's the next line for you, exactly. So, yes. So those two channels differ in efficiency, and you will hear that that channel is much more efficient producing double black holes per unit mass. Okay, and that's that's true, but that's why I have this number, how big difference you have in a mass of stars, to oppose to efficiency. So this is that x means a number of double black holes you produce per unit mass, per solar mass. Okay, so typical number in a population isolated binary evolution is 10 to minus 7. Just look at this number for now. For dynamics, it's 10 to minus 4. So it's 3 orders of magnitude more efficient in dynamical channel. You have also 3 orders of magnitude here. In mass, you would come out even. Then both channels are equally likely to produce double black holes. But that's a conceptual mistake. People don't take into account that the 10 to minus 7 is based on our galaxy, which have high metals. And I told you, high metals, stars lose a lot of mass, they produce low mass black holes. When you look at universe as a whole thing, when was the peak of star formation? Does anybody know? Redshift of what? 2. So that's 8 billion years ago. Now we're dying, we're going apart, stars are flying away, we're dying for 8 billion years already. At redshift 2, what was the average metallicity? Does anyone knows? 10% solar. So instead of making 10 solar mass black holes, like in our galaxy, you make a 40, 30 solar mass black holes at the peak. So when you take that into account, the formation efficiency, 10% solar metallicity is 10 to minus 5. So when you compare that number with this number, and so it's order of magnitude difference. So you produce maybe 10 times more per unit mass in global clusters than in the galactic fields. However, you have 3 orders of magnitude more stars to make black holes with. So you win. And you see that in rates. So when you do binary predictions, and I will show you those rates, you get numbers of the order of about few hundred double black holes per gigaparsec cube per year. So that's from binary evolution. And here you get few, 5. Typical number is 5 per gigaparsec cube per year. You can get maybe, with this channel, you can get to about 50. With this channel, you can overproduce double black holes. Of course, you can kill all of them as well. There's no problem in killing black holes, okay? For comparison, LIGO rates are 10 to 200. So, you know, those are slightly overproducing the double black hole rates, and those are slightly underproducing. But they both fall in within that wide range that LIGO and Virgo is seeing. So that way, those both channels are viable channels for explaining LIGO observations. We I want you to understand the difference. But what Harold said, it's true. This is more efficient channels for making double black holes, but you need to take into account low metallicity stars that are present in universe, okay? Okay. Now the other channels, and I'm just gonna go through names because I'm sure Ilya made, you know, story out of that. There's a population 1-2 channel which involves rapid rotation. Stars evolve very differently when they rotate because they mix all the fuel into the core. They don't expand. They form double black holes in a different way. People think that you need strong tidal interactions for those stars, and you can estimate how many of them are close enough, one star to another, to be tidally active. And that's about 10% by mass of stars. So it's 90% in regular evolution, wider binaries, and very close one, it's about 10%. Then you have population 3 stars, and I'm going to make a case about this in a few slides. They can produce also double black holes, but there is not much mass in those population 3 stars, about 1%. I will do that estimate for you, okay? And there are claims that those could be significant contributor to LIGO Virgo. No way. It's orders of magnitude below LIGO rate. Then there's a primordial black holes, which not many people believe in astronomical community, but there's a whole community that just talks only about those. They just think LIGO cannot make, I mean, that community doesn't believe that stars can make 30, 50 solar mass black holes. They are focused on those 8 solar mass black holes that we see in our galaxy. So for them, it's evidence that those LIGO black holes are primordial. And then there is number of exotic channels. You can have, you know, kind of, you know, oversized global clusters, which are called nuclear clusters, that sit in the center of some of active galaxies. It's like a huge global cluster around a central massive black hole. So they could produce dynamic double black holes. You can have massive star formation in AGN disks, and then the friction in the disk will bring a binary together and make those black holes merge faster than in a typical isolated binary evolution. Or even people propose, you know, single star that can, you know, rotate very fast, the core can split. It's totally unphysical, in my opinion. The fluid doesn't, the gas doesn't work that way. But anyway, it was proposed. So there's a bunch of channels, and now I'm gonna use actually. So I'm not gonna discuss any of those. I'm gonna use those two to make the first point, the first issue. Yes, please. No, that's a mass of a progenitor in star. And I looked back in time. That's a big bang, and here in present, I look back in time. I integrated the star formation that I see. So like in a light cone of LIGO, that, you know, so that would be that many population 3 stars, that would be that many population 2-1 stars. Stars, not black hole masses. But that translates to rate directly, because, you know, each channel gives you efficiency per unit mass. You also need one more factor that I didn't mention here, but I will bring it up: delay time distribution. if delay time distributions vary between some channels, it may give you it's not enough to have just formation efficiency per unit mass, you need to have delay time. Of course, if they form far, far away. Yes, yes, of course. So for these events, this is so binary stars is about 50%, okay? Factor of 2, I don't care in those estimates. I really care about orders of magnitude, and I will really, like I did mention, there's a lot of uncertainty in stellar evolution, in dynamical evolution, in all those channels. Sometimes we even don't know if those channels even work. So factors of few doesn't matter. I will be operating, I'm an astronomer, orders of magnitude. Okay, so let me bring the first issue. Just by the virtue that we have at least, we have more, but we have at least 2 channels, let's use binary evolution and dynamic double cluster, that can explain those massive double black hole mergers. It means that we don't know the origin of those double black holes. And it also means that our inferences of information from the Ligo observations are very limited, because each channel has a separate set of conclusions. Here, I will walk through, not through this picture, but a similar picture. I'll tell you about all those stages involved in forming a double black hole. But here we learn something about possibly mass exchanges between 2 stars, while here in global clusters we learn about dynamical evolution, dynamical interactions of stars within a big systems of about millions of stars together. To form double black hole in global cluster, that particular example requires about 40 interactions between different binaries and triples and single stars. So you have a very different set of conclusions here if you say that those LIGO black holes come from dynamics, and you have different set of conclusions when they come from binary evolution. And of course, why would they come from one channel? Most likely it's probably a combination of channels, and we don't know at the moment what combination and which channels. So that limits conclusions that you get. There are some conclusions that are above that divisions to channels. Let's say if one, like I said, I'm gonna work on the assumption that those black holes are made by stars, not primordial. So this tells you that if you get 30, 50 solar mass black holes, they must come from low metallicity, because otherwise the mass would be blown out by the winds. So that's one conclusion that's above the channel. You can do something with spins as well. So you have to be very careful how you present the conclusions, and if you have conclusions specific to the channel, you should always make sure that this is understood, that that conclusion, that implication is within a channel. And actually a lot of people think that we will be able to use spins to differentiate between channels, because masses and rates you cannot do. Masses you can do in both channels, rates as well. So spins, but I think LIGO will not do it. We'll need LISA or Einstein telescope or something else to do that. But I'm being told I'm pessimistic, but it's actually good news for you, because you will be solving those issues. Some of us will be already retired. Okay, so that's the first issue. Just, I would laugh if we can show that, some system comes from dynamics or global cluster, dynamics or field evolution or different type of evolution, but we don't know that at the moment. At the moment, we simply don't know, okay? Now, let me go. So I'm gonna now spend few slides on this channel. So just take this into consideration. I'll be giving you, let's say we can show that this channel is the dominant channel. I'm not saying all of them, but it's a dominant channel to explain that rate. And my idea behind that, of course, I'm a proponent of a channel because I work on it, so I'm biased here. So I'm warning you, it's a biased view. But let me make that argument for you, and you can take it the way you like it. So this is the rate. So I'm getting those rates or even higher rates. Global clusters are getting those smaller rates. Where is a peak? Peak, starting from the very first detection, the first black hole, peak is at 100 per gigaparsec cube per year, okay? And it stayed with all those detections that we have right now, it stayed at 100. 100 is very hard to get with global clusters. It's very, very hard, even with that more efficient binary double black hole formation, okay? 100 is very, very easy for binary evolution. I just need to kill 7 more stars in common envelope or just give black holes 50 kilometers per second kicks. And nobody can exclude 50 kilometers per second kicks. Actually, I checked those two systems that we talked about with C yesterday, Cygnus X1 and GRS 1915. Upper limit on Cygnus X1 is 60 kilometers per second for natal kick. It's totally consistent with 0 as well. But that's upper limit. For GRS 1915, it's 75 kilometers per second. So I give my black holes 50 kilometers per second kicks, my rate goes down to 100. You know what happens with this channel if I give black holes 50 kilometers per second kicks? The rate goes to 0. They also don't, and global cluster people don't advertise that. They have no black hole kicks no matter what black hole mass. You give 50 kilometers per second kicks to black holes, they escape that's the escape velocity of a class from cluster. They go. So it doesn't go all the way down to 0, but it goes to negligible number. So that's why I will be, but anyway, I cannot prove that this is a channel, but I'm gonna give you conclusions that are, limited to that channel for now. Okay? So let's do a few slides. So let me tell you how we do simulations. So we do simulation with population synthesis. We follow evolution of stars in the universe. So we start with population 3 stars, born about, 400 million years after Big Bang. We, evolve them with low metallicity, no metals with very small stellar winds. They form typically more massive black holes, but they're still subject to population, to per-instability supernovae, so they don't form black holes above 50 solar masses, okay? Then, they enhance the gas clouds with metals, and then second population of stars forms, so we have a peak of star formation, this is time. So, 3-5 billion years after Big Bang, you have peak of star formation, that's redshift 2, and then you have a population, 1 stars that are metal enriched. So you follow all those stars, and let's say you form a binary here, it evolves and forms double black hole here, but then that black hole will be, let's say will be separated by about 40 solar radii. It takes about Hubble time to merge them. So those black holes will be going around each other for all those billion years, and bam, they will merge close to Milky Way. And then LIGO can see it. So you do that statistics, and you can. So what we do, we follow that evolution, and on Earth we put an actual detector, LIGO detector with sensitivity curve, specific to O1 and O2, okay? And for each merger, we put a waveform from LIGO. So we actually do the synthetic detection. So I will be presenting you kind of detection weighted probability. So all those issues with masses, with the in spiral, ring down, merger. So we include waveforms with in spiral, ring down, and merger. And we have LIGO sensitive band. We take all of this into account to calculate how many of them we should see. Okay? So that's a self-consistent way of doing that. What people did before, years before, when they were getting different answer, like they were predictions before 2010 were showing that neutron stars should dominate the signal, which we know now it's not true. What people did, they took Milky Way with those low mass black holes and they estimated number of neutron stars and black holes. Numbers were kind of similar. Well, I mean, black holes were lower, but they pretty much overproduce neutron stars. I mean, in our galaxy, there's more neutron stars than black holes. Okay, so when they extrapolated our galaxy to the entire universe, which was wrong, I was responsible for that as well. We're getting, neutron star merger rates, detection rates higher than double black holes. But when you take those populations of low metallicity stars, double black holes simply dominate. That's the main effect here. Okay. There's one more evolutionary effect. I'll come back to that in a second. So how do we deal with, there will be a very legit question. How do we deal with, what was the star formation rate? What's the chemical evolution of those stars which comes into the model? Those are major ingredients here in that type of estimate. So, well, we don't know, it's astronomy. We know things kind of locally. We go farther down, down in redshift towards Big Bang, it becomes more uncertain. But we do have estimates. So first estimate is for star formation rate. It's so-called Maddow plot. Here you have redshift, that's the present time, and you go towards Big Bang. And here you have star formation rate in universe in general, not per any given galaxy, in universe, taken from a lot of different type of observational data. So this star formation rate is how much solar masses you produce per megaparsec cubed of co-moving volume per year at a given redshift. So for population 1, 2 stars, you probably know that plot. It goes up to redshift 2, like we said, and then it drops down. We don't know how steeply it drops down because we don't know how to correct for extinction at high redshifts. Probably the answer is somewhere in between. For my estimates, I'm using that low curve, so I'll be kind of, not overproducing. I don't want to overproduce the black holes. I'm still kind of overproducing them, but I'll be using that curve. So, population 1, 2 stars were peaking at redshift of 2, and they began forming somewhere around redshift 15. 10, 15, we don't really know. And then population 3 stars, orders of magnitude below, they started somewhere redshift 20, 25, 30, 40, we don't really know. This is highly uncertain. They definitely were forming somewhere around 20. They peaked at around 10. They could not go higher because reionization would happen much earlier. So we know from Planck results and from some other observations that they could not go higher than that. Actually, I already overdone that star formation in population 3 because I wanted to see what my maximum rate of double black holes for population 3. Usually people use the rate which is 1 order of magnitude lower. So this is just to make the conservative assumption on on comparison of population 3 and population 1 and 2, okay? And I'll come back to this. So when you actually integrate the mass under one curve and the other, you get the mass under population 3 about 10 to 18 solar masses, and for population 1, even for that lower curve, you get 10 to 20. So at max, you get 1%. Most likely it's 0.1% of mass. Well, it is based on some arguments with reionization, but it's cosmological simulations. You're right. Yes. Yeah. The people look at gas, look at GRBs, at supernovae 1A rates, supernovae rates. People look at AGNs. Let's say you see some stars and gas with high metallicity at redshift 7. They put all of this together. A lot of galaxy observations with metal estimates and start from, they just look at blue light at high redshifts. So this is all put together by Piero Madao and his collaborators. Like I told you, Paweł Krupa does IMF, Piero Madao does that type of thing. So there is a lot of observations going into this. But it's still highly uncertain. Up to redshift 2, we're pretty good. But you see, beyond redshift 2, 2 orders of magnitude. And this is just an upper limit, really. And shape is not really known, okay? So, but this is kind of well measured. Well, it's semi-measured. Now we get to an even bigger, uncertainty. It's a chemical evolution of the universe. So, universe is very pockety. Like you have even in our galaxy, you have pockets of high metallicity or pockets of low metallicity. So it's not uniform. But in simulations, I cannot really, I haven't got to that. You could probably simulate this. We try to simulate the average metallicity increase throughout cosmic time with some distribution at each redshift. So what we use actually, you also can try to estimate that. You look at the gas, you look at the number of, emission and absorption lines, so you can look at metals at given redshift, and you can make some estimates. So this is again redshift, and this is log, decimal logarithm of metallicity in units of solar metallicity. So pretty much 0 here, we have solar metallicity, okay? So that red curve is taken again from Maddow and Dickinson paper 2014 when they look at a bunch of observations and simulations as well, chemical models of enhancing the interstellar medium by stars. And you see that that's a mean metallicity. It increases with time, from after the Big Bang to now. So I employed that model. Someone can employ the other model. The rates will go up and down. Evolution of stars will change. But I think you won't get that far away probably from that model. And at each redshift, I would assume that mean metallicity, but would also assume a Gaussian distribution. I don't know what the distribution is. Nobody really knows of metallicity at given redshift, especially at redshift 8, 6, or 4. I just assume Gaussian. But so, I have to put some things almost as a toy model, but those are kind of educated guesses. I know the metallicity is not just one value at a given redshift. It has some broad distribution. And it's about, more than order of magnitude, okay? So that's why I did, 2 orders of magnitude. And then I employed that model, and then I evolved all those stars in the universe, and then I counted how many black hole neutron stars and neutron stars I get. So I'm going to show you that plot. Again, just binary evolution channel, okay? I'm talking about that one channel. So this is the main plot with results. So I'm going to spend 5 minutes on this. We're doing still good on time, yeah. So first, let's look at the rates. Let's just look at that right panel right here. It shows only double black holes. So I'm only talking about black holes. We'll be comparing the rates to LIGO, which is 10 to 200 or 102. That blue rate, so here, it's a pretty much merger rate density that I get from simulations. Those are all those colors. But the blue one, just so to guide your eye, the blue arrow shows the extent of the LIGO measurement, okay? And I have, you see, bunch of models. Some are above the LIGO estimate, some are below, so I can already exclude that. And I have a bunch of models that are within the LIGO rate, okay? And they mostly differ, actually, in this estimate, I mostly differ black hole natal kicks. So those high models here have no black hole kicks or very low black hole kicks, like, 0 to tenths of a kilometers per second. And those models that give me low rates have high black hole natal kicks, hundreds of kilometers per second. So binaries, when they form, when one star explodes and the rest forms black hole, that black hole gets a large kick and binary gets disrupted. That's why the rates are low, okay? So, we're doing good on rates. We can actually, if we know that all LIGO black holes come from that channel, and if we could exclude any other uncertainties, which we cannot, but if we could play the game and try to estimate a black hole natal kick. But the life is not that easy. We have about 20 other parameters that we could adjust in a different way. And with 20 or 30 parameters, nobody has explored entire parameter space. It's impossible with current computers. Even if one model takes just a week on one computer, with 30 parameters, 30 dimensional space, people do the most. Grzegorz, how many models have we done? 1,000, 2,000, 10,000. But it's still a drop in the sea. So I think Ilya probably brought this up. He's trying to map parameter space in some places and interpolate in between, guess in between. So we're trying to do brute force and get as many models as we can. Ilya is trying to play smart and estimate how that parameter space will look like to see if there are any big minima that we have or maxima that we have missed. But that definitely needs exploration. But that's a way of thinking. If you can say that some parameters are not really important, you can eliminate them. And let's say those are the three most important things. Let's say common envelope, black hole natal kicks, and say, some initial conditions of simulations like initial separations. You can play with those. So here I just made it one-dimensional. I just played with the kicks, and it tells me that, if LIGO is about 100, the black hole kick should be about, 50 kilometers per second, which is consistent with all the current observational data. Okay, anyway, that's how you can play that game with rates. But now the second most important parameter, it's mass. So, you want to ask, okay, LIGO sees, I'm going to use 6 events because I'm going to use LVT also as an astrophysical black hole. I know it's not claimed as a full detection, but more and more people believe it's astrophysical, and you have masses of compact objects in each detection. So 12 plus 7, 14 plus 8, 23 plus 13, 31 plus 19, 31, 25, 36, 29. So for double black holes, especially those massive ones, okay, I will correct that. But the masses are right, is that right? Yeah, so I don't care about those numbers. Yeah, but masses. Well, you can. I don't. I want more of them. In the end, I just want distribution of masses. But LIGO gives me 6 events. For those double black holes, I will not look at a chirp mass. I will look at a total mass because it's especially for the massive ones, it's better measured quantity. So I took total mass. I added the map and I also redshifted them. So I get observational quantity. Redshift is 0.1, so I multiplied, that by 1.1, so it doesn't. It's pretty much, that mass, and I plotted all of them here. All those 6 events are here. So this is a total redshifted mass. So it goes from about 20 to about 70. Okay. So those observed events. Now I have also plotted with a blue line. That's a LIGO O2 sensitivity for 120 days. This is, by the way, this is a merger rate density, so those points have no meaning. I mean, this way. They only have meaning on that axis. But that curve actually gives you, that's a volume times time that LIGO was watching for 120 days at O2 sensitivity. It gives you, what an upper, it gives you a sensitivity and pretty much a limit on the rate that LIGO could have seen. So my predictions needs to be above that limit or close to that limit to give me detection from the model. So now I'm giving you two models, here and here, magenta and red line. So you see the generic shape is about the same. Those are distributions of double compact object total masses as come out, redshifted as well, as come out of my models. Okay? Or not only my models, there are similar results from other models as well right now, so from basically generally evolutionary models. So what you see, so the different mass beams, the first mass beam is between 1 and 2 solar masses, those are neutron stars. You see how we are way below the detection, and the detection was made, so we are totally off, and I will come back to that point on the last few slides, okay? We are totally off about neutron stars. We're not predicting any detections at the current sensitivity. We just don't have enough. We don't produce enough of them. That's a big issue. Then the next few things are black hole neutron stars. We also do not predict detections. But once you start going to black hole regime, which are those massive systems, we do predict detections. And we predict them, you see, where the detections were made. The red line is close or above the blue line in that region between 20 and about 80 solar masses. So not only the rates agree, also masses agree when you look at total masses. So, this is kind of, and that was done pretty much before LIGO. I mean, that plot is actually done after the LIGO, obviously, but we had those predictions before LIGO. So in that sense, actually, I trust LIGO detections because they confirmed that stellar evolution works. I know it's maybe not the way you used to look at the LIGO data, but that's actually comforting. That's something, there's so many caveats in stellar evolution, but with stellar evolution that we actually, some of our estimates are not as bad as one may claim, or one may think, okay? So we have some of those predictions. Okay, but that's about things, good things that we understand. Now let me get away from that and get to the issues, okay? Well, I have on each model I have so many other parameters I can play. But yeah, it's close to LIGO low rate. Yeah, because this is statistically, this is not statistically precise picture. Pretty much, you predict detections whenever you have the closest between you closest to the blue line. You have to, I change the beam size, my things go up. So I can change that beam size and beam them differently, and I will get closer in. So this is just to guide your eye. So I should have said it differently. I was not expecting that anybody will catch this, but but the statistically correct statement here is, I expect detection in places when that line is the closest to the blue line, or the highest above for models above. Yes, you can. That's why this is to show mass distribution, but then I integrate entire curve which is independent of binning, and I can get the rate estimate. Okay, this is really, Ilya had a huge problem with that plot because it's statistically incorrect, and you're very right. It's really just to guide distribution in which range of masses you expect detections, most likely. I cannot exclude detection here or even neutron star. It's just less probable than in this range. Because you have mass distribution and you would think it peaks here. But sensitivity, it's just to tell you how, sensitivity changes this way. If I didn't show the blue line, you would think that, the peak of that magenta distribution is here. So you expect detection here. No, you have to compare relative to what LIGO can detect. And LIGO is very sensitive to total mass or chirp mass. So here you have a great distance between the two curves, and here you have much closer distance. That's the only way I wanted to guide that. A lot of people wouldn't understand. They would see the peak and they expect detection right here. No. Okay, anyway, let's go to the issues. So, when we evolve stars in that binary evolution channel, I will come back to that plot in a second. I just want to show you that when in binary evolution we start with stars far apart. Those stars that make black holes are 50, 100 solar masses, typically 20 solar masses at minimum. Okay, so those stars on main sequence, you can think of, star mass has about, it's 50 solar masses, so on main sequence would have about 50 solar radii. So if you want 250 solar mass stars or 200 solar mass stars, you need to have orbit at least 100, 200 solar radii just to fit them on main sequence. But even on main sequence, they will increase their size at least by a factor of 2. They will become 200 solar radii stars. And then beyond main sequence, if they don't rotate at breakup velocity, they will just go like, sometimes to 1,000 solar radii. So you need large orbits to fit those stars, unless if you put them on a too close orbit, when they start expanding, early on they will merge. They will form one massive single star. And so they will form a massive single black hole or per-instability supernova, but you won't form double black hole. So you kind of want to put them far apart. And typical distances that we find that lead to double black hole formation are about 1,000, 2,000 solar radii. That means you start at the size of half of a solar system. You somewhere at the Jupiter-Neptune orbit. But if you put two stars that far apart, and if you collapse one and the other to black hole, let's say a 30 solar mass black hole, they will never merge in a Hubble time. The emission of gravitational radiation of two objects going that far apart, it takes too long. You need to bring them down to below 50 solar radii, to below half of a Mercury orbit. And then 230 solar mass black holes will merge within Hubble time. So you need a process to bring them together. And in binary evolution, it's called a common envelope. And did Ilya actually make that case how common envelope works? He did make it, or should I make it one more time? Okay, so let me just make it shortly. So imagine you already formed one black hole, and you have a second massive star, like a 50, 100 solar mass star. That star stays kind of compact during main sequence. After main sequence, it will start expanding. So the core will collapse, in the response envelope will expand, okay? If black hole is relatively nearby, that envelope will engulf the black hole. So that black hole will start actually seeing the gas of the envelope of other star. So it will push through that gas, and by friction, it will start slowing down. So it will start in spiral and will go in. But friction will, that's a big shortcut, will put a heat into that envelope. That envelope will heat up, will puff up, and will try to go away to infinity. So that's a way of ejecting binary orbital energy into envelope of that star. If you have enough orbital energy, if orbital energy is higher than the binding energy of that envelope, you can remove that envelope, but then the core of that star and the black hole will get much closer in because you use some binary orbital energy. So that's the process. Many times the thing will merge into single star. Many times you will reduce the orbital energy, but it will be, let's say, 100 or 200 solar radii. So it will not merge within Hubble time. But you have a sweet spot and a lot of stars to work with in the universe to actually make it happen to about 30, 40, 50 solar radii where you want it. Okay? And you only look at those. We don't know how common envelope works. Nobody has successfully simulated common envelope in hydrodynamical simulations. We don't have computer power to do that. It's orders of magnitude in different quantities to do common envelope problem. So this happens much later. So star formation will happen even before main sequence, way before main sequence, when you have a protostars. So you don't expect much of that initial interstellar cloud to be around when you have common envelope few million years after. So you pretty much, it may be some leftovers outside of a binary, but you're talking about really that common envelope happens very close to those two stars that have formed. Yes, we finally, after years of searches, we do see some binaries decreasing period and then going red nova. Like the one thing just the orbital period just disappears, and the two stars become one star, and the star puffs up and becomes red. So you use kind of those kind of like a there's like I forgot the phone number of it. So it's like V53 Monocerotti was a prototype. So there are some binaries that there's like five of them right now. But so you see the star going in, and the star gets red and bigger, and that just was last couple of years, and people are watching them. But those stars are way less massive than those. No, no, you just see the envelope, the expanding photosphere. That's it. The other star just disappeared inside the other one. So it's like, five cases right now. Last 3-4 years of observations. Okay, but not for massive stars. It's like way below 10 solar masses, like few solar masses stars. So that common envelope. So just to give you the flavor of uncertainties we deal with. We don't know. So we don't really, well, you don't observe common envelope. You only observe the onset of a common envelope. The time scales, people were, I will give you the historical overview. People were thinking, 100,000 years, 10 years ago. Then I heard 10,000 years. Then a few years ago, 1,200 years, and now I hear a few orbits. Okay? So that's the state of the art in common envelope simulations. We know that common envelope works. We know the class of stars which are called pre-cataclysmic variables. That's a hot white dwarf and the main sequence stars. We have hundreds of them, not thousands, hundreds of them on a very close orbit. They must have just came out of a common envelope. So we know it works. We just don't know how. So this is a highly uncertain part of the issue. And if, let's say, somebody told me that could prove to me that this channel doesn't produce double black holes, I would say that common envelope is so messy for those massive stars they never survive. That would be my way, the best case, to kill all those double black holes that come out so naturally out of that process. Okay? Yes. Is that Ivanova at all? Yeah. Is this Ivanova at all? Yeah, so for you guys, so if you guys want to read on common envelope, what Svi is suggesting is probably, like he says, the best paper, Ivanova et al. 2014. Okay? So go look it up, and it's a good read. Almost like a novel. Okay, anyway, let me show you what, okay, so we know it's highly uncertain, so you already got that. Now let me show you what difference it can make in double black hole predictions, okay? So let me make one more point. When you have two main sequence stars, there's pretty much two uniform ball of gas. When one main sequence star, the smaller one, enters the envelope of or outer regions of a more massive main sequence star, you start in spiral, but you will never end. You're pretty much heating up entire star because it's a uniform ball of gas. So you never eject the envelope and you form a tighter binary, because you always go to the center. You form one fastly spinning main sequence star. On the other side of spectrum, when you have a giant star with a very dense core and the very rarefied envelope of gas, when you enter, you just hit the envelope and you can eject that envelope, okay? And you can survive. You can still die if you don't have enough orbital energy. You can go all the way in, but you can, in some cases, you can heat up just the envelope and eject it. There's one case in between, which is evolution just right after main sequence. It's called Herzman Gap. It's for physicists. This is a part of Herzman-Grasse diagram that astronomers use to classify stars. But this is evolutionary phase when you stop burning hydrogen into helium in the center of a star. So the core is already formed. and then, but your envelope is still kind of dense. It's just starting expansion, okay? As it happens, the most of the expansion, so the biggest chance for common envelope is right during that phase. So let me give you an example how it works. So it really changes. So a lot of common envelope is expected in that stage, and we don't know how to treat that. If this should be a common envelope, could you survive? Should we treat that event as a two main sequence stars, or rather as a giant star with very defined envelope and core? We don't know. And the changes. So here it's a time, evolution, and radius. So evolution of radius in time for a 30 solar mass star. It could make a black hole, okay? So this is main sequence, so the radius of it, so this is for two metallicities. Let's first look at solar metallicity. So first on main sequence star expands a bit by a factor of about 2 on main sequence, and then it almost explodes radially. After so the core collapses, envelope expands, and that happens on the Herzman Gap. And then it goes to core helium burning, and it's slowed down expansion here, okay? So you see, most of expansion happened right after main sequence on the Herzman Gap. We simply don't know if common envelope could be survived, because we don't know. Pretty much there's not much of a boundary between core and envelope. So when you start hitting the envelope, you may be hitting an entire star. That's one issue. Second issue, some people think it's Pawlowski's, again, Ivanova student, who made the calculation, and he says that even if some people think that should be a common envelope event, it should be rather a stable Rorschach overflow event. So you actually don't expand so much with that star because it has radiative envelope. So you take a bit of a mass of the star, dump it onto the companion, and the star, instead of expanding, contract. So you can have a stable Rorschach overflow, and that leads not to the orbital contraction, it leads actually to orbital expansion. So instead of forming tight binary to make you a merging double white dwarf, you make a double white dwarf, which will never merge in a Hubble time. So we have all those issues, okay, at solar metallicity, and most of the stars don't produce double black holes. Not only the black holes are a lower mass, but there is a small efficiency of double black hole production through common envelope. Now look when you go to lower metallicity, 10% solar, 0.1 solar. Same star, it just evolves slightly differently because of opacity issue that I mentioned yesterday. And now, this time, Herzman Gap have a rapid expansion, but smaller. Star doesn't expand so much because radiation pressure doesn't push against those metals that are present here, and you stay more compact. And then you change to core helium burning when you have already well-developed core envelope structure, and you have convective envelope. So when you actually start mass transfer, when you take a mass from the star and dump on a companion, star, instead of contracting, will expand and will swallow the companion in. So that will be, you see, you can have a common envelope in a broad range of radii. This is logarithmic scale, 10 solar radii, 100,000. So in low metallicity case, you expect actually a lot of interactions between stars to be common envelope, and a lot of them will be successful. When you actually calculate, if I take, a bunch of stars at this metallicity solar and at this metallicity, I will produce about 50 times more black holes than here. So 50 to 1, sometimes even 100 to 1, at least 10 to 1. So let me finish that statement. So not only that black holes are of heavier mass, so LIGO can see them farther out, but binary production efficiency is almost 2 orders of magnitude higher. And this is what I showed you when I was showing you those different when I was here. That's the difference. 10 to minus 7 solar metallicity, 10 to minus 5, it's at low metallicity, okay? It comes from common envelope. Okay, I'll take a question now. It probably was too fast. Okay. So it's in a first order, a zeroth order answer, it's a matter of mass ratio. If you have a very massive star, and a very low mass star, that massive stars will tend to dump so much mass onto that low mass star that low mass star cannot accumulate that mass. It will accrete, or that low mass black hole will accrete, let's say, even 10 times Eddington limit, let's say, or even 100. But if you dump much more than that, the mass will start building up on top of the black hole. And in the end, if you keep dumping so much, eventually you will build a common envelope. If the mass ratio is more equal, let's say you have a 10 solar mass black hole and 50 solar mass star, massive star, the mass transfer is kind of, about Eddington or so, or slightly over Eddington, and black hole can actually accrete most of its mass. So then the mass transfer is stable. It doesn't lead to common envelope. So it's the first order, it's a mass ratio. Then second order, it's what type of envelope that star that is dumping mass towards black hole. What type of an envelope? If it's radiative envelope, you take some mass from radiative envelope, it shrinks. So mass transfer goes down. So it stabilizes the mass transfer. But if it's convective envelope, when you so you get a convective envelope at later stages of evolution. When it's convective envelope, you dump some mass onto the black hole, and the star expands, so it wants to dump even more, and you accelerate that process, and you go to dynamical instability, you go to common envelope. So that will actually goes nicely with that picture, how we evolve those two stars to become double black hole system. So you start with two massive stars at low metallicity, it's like few percent solar. One is about 100, one is about 60 solar masses, but those are about almost equal mass stars. So when the most massive stars starts expansion after main sequence, mass transfer is stable. It's at a high rate, but it's stable. And you dump some mass onto that star, some is being lost. By the way, that's a Martina picture. Martina has done that plot. Am I right? Yeah. So this is like a cartoon, but this is how we think those stars evolve. We don't know. That's how we think. That's how we do predictions. So we attach some of that star mass onto that secondary. It rejuvenates. It becomes more massive. It becomes from 60, it becomes 70 solar mass star. The rest is lost from the system. And you deplete the entire envelope, but it was stable. You don't have common envelope, so separation didn't change much. It went from 5,000 to 3,000. It did shrink a bit because we ejected a lot of mass, but it's 5,000 solar radii to 3,000 solar radii. This is not a separation that you want. You want to get to about 50 solar radii with those two stars. So when you deplete envelope of that star, that primary, that more massive star, you expose a helium core, which we call a Wolf-Rayet star. That's about 30, 40 solar mass Wolf-Rayet star, very massive star, very hot. And then that star lives for about 100, 200,000 years. And with that mass, we assume that it collapses directly to a black hole. You lose some mass in neutrino emission, few percent. We assume no natal kick, so no kick, no mass loss, nothing. It just in place collapses to a black hole. So it forms about 33 solar mass black hole. And we assign it, we calculate a spin for it. We could actually follow evolutionary models of those stars with angular momentum assumed angular momentum transport with initial rotation, and you can see how much angular momentum we have contained in that collapsing core. And for those models, we actually assume that most of angular momentum was removed with the envelope from that star. So initial black hole spin is about 0, close to 0, 0.1, 0, we don't really know, but it's very low, okay? So you form a black hole. Now, that goes to that question of mass ratio. Now you have a 30 solar mass black hole and about 70 solar mass massive star that's twice more massive than a black hole, more than twice, and that already leads to dynamic instability. So that star, when it expands to fill its Roche lobe and to start dumping mass onto black hole, it's already during core helium burning. Its envelope is convective, mass ratio is high, and this thing is not stable like it was here. It's dynamic unstable, and that you dump mass, it builds up, and you keep adding more and more, and finally, very quickly, people think you have a common envelope. And then you do your magical treatment, whatever treatment you want, but you need to remember, you have a lot of stars in the universe, and you have them on a very wide range of orbits. So really, no matter what prescription you want to use, you always end up with some double black holes. That's why this channel is so prolific in making double black holes and getting high rates. Of course, you can fine-tune things to kill things, of course. But if you try to play with the prescriptions that are available on the market, you always end up with a large population of double black holes. So anyway, the main effect of a double black hole is that you remove envelope of that star, so you're left with a Wolf-Rayet star of about 30 solar masses, so very similar to the one that was formed out of primary. And also, you go from about 4,000, 3,000 solar radii orbit down to 30. It is 2 orders of magnitude decrease in orbital size. You just compare, we can estimate a binding energy of a common envelope, and we remove this from orbit, and that's what you end up with, 30. This is exactly your sweet spot. We have thousands of binaries that don't make it, but I'm showing you one that actually makes it, okay? So now you have a closed systems black hole and a Wolf-Rayet star. That Wolf-Rayet star is living also about 100,000 years. And again, we assume no black hole kick. It collapses directly to a black hole. Since it's a lower mass star, maybe it has not removed all of angular momentum, all its rotation by winds, because it has lower winds. It's a lower mass star, lower winds. So we calculate angular momentum content of that star, and we get a black hole spin, initial spin 0.14. Okay, so it's also small. So you form 2 black holes at about 40 solar radii orbit. One has spin close to 0, one is 0.1. Okay, and then you have to wait. So that entire evolution to formation of those 2 black holes took 4.9 million years, 5 million years. That's a typical evolution of 2 massive stars, 5 million years, 3 to 5 million years. But then on that orbit, you have to wait 6 billion years for that system to merge. So those black holes will be going around each other, and they'll be emitting gravitational waves at a very low level. So the orbit will be shrinking, shrinking, shrinking. It will accelerate, and LIGO will see only the final part. But to get to that final part, from 40 solar radii, takes 6 billion years. It means that star was born close to a peak of star formation rate at low metallicity. That's how you make those systems, okay? And this is very important in those predictions. So now, evolution works like this. That's what we think in that channel. But I wanted to discuss the final issue here, issue of spins. So we talked about black hole masses, that some channels can do it. We talk about rates. Rates can be also explained. But now spins. That's a final thing that LIGO measures. So LIGO doesn't measure directly black hole spins. It measures something that is called effective spin parameter. Was it defined? Was it explained? Yes. So just to bring that definition on a blackboard. So I'm bringing it here because for that part, so here that plot actually shows the formation of a black hole with 30 solar mass black hole and 20 solar mass black hole. That corresponds to this event, GW170104. So that was discovered in January 2017, and it was claimed that possibly, or actually some people were saying very likely, or some people were saying it just comes from dynamics, okay? And it was due to the fact that LIGO measured mostly negative chi-effective. I would call it that effective spin chi-effective, okay? So it means that most likely one of a black hole, so let's say binary orbit is in a plane of a table. So binary angular orbital momentum is here. So if 2 spins are aligned and are high, then the chi-effective is 1. That's what you kind of expect in binary evolution channel. You have 2 stars rotating with orbit. If black holes form through direct collapse, you don't change black hole spins. So if black holes have large spins, you would expect chi-effective positive at a high value, okay? So then it's hard to explain negative values to start with. Of course, if one of the black hole kicks can, if you have black hole kick, it can, misalign the thing. Then you can even get to negative, but it will be hard to get a lot of them negative, probably few, okay? So people were claiming since, LIGO were measuring values minus 0.4 to 0.1, and it's mostly 80% of the probability distribution is negative, that systems must have come from dynamics. In dynamics, you pretty much have one black hole. I'm gonna make a very big shortcut. It doesn't work this way, but you have one black hole, another single black hole. They go, do their thing, and they catch each other on some orbit. So totally random spins. So it's very easy actually to make high negative spins. It's as easy to make positive spins, effective spins, but it's very easy to make negative, okay? So that was the claim. So the solution to that was, if you look at that system, if you make spin magnitude small, okay, you can also make this very small and consistent with that value. And that's what we exactly showed here. you can actually have a model of a given angular momentum transport in stars in such a way that will produce black hole spin with very small values. So here black hole was formed with spin 0. Oh, actually I didn't mention, the black hole accreted about a solar mass, less than solar mass, but it can accrete, black hole can accrete about 1 solar mass in common envelope, okay? But you don't spin up black hole by much, by accreting that little mass. To spin up black hole significantly, you need to accrete about as much mass as black hole weighs. Okay, if you accreted 20, 30 solar masses on a 30 solar mass black hole, you would spin it up from 0 to almost 0.9 or 1, spin parameter 1. Okay, since it accreted only 1 solar mass, it got spun up to 0.05. Okay, and the second black hole was formed with a spin 0.114. It didn't accrete any mass because it cannot accrete for another black hole. So when you calculate actually for this system, you take masses, you take those spins. When you calculate effective spin parameter here, it's 0.09, exactly within a 90% Ligo credible limit. So we have a system that in binary evolution that can explain that thing. Of course, if you look at likelihood, it'll be more likely to make such a system in dynamical formation scenario, but you cannot exclude binary evolution based on that type of prediction. Okay? So that's one issue, that some of those claims that that system must come from dynamical are not right. Most likely, but not you cannot prove that. But okay, let's look at our, so now the issue we have with spins. Because if spins are small, we won't be able to tell dynamical channel from classical channel, really. So how do we come with that spin model that, you know, spins are small? And I will show you what are the other observations of spins of Ligo and how that compares to those models. So we pretty much used detailed evolution models from Geneva code. There are really two major codes, of more than two, but two major codes are MESA. It's a detailed evolutionary code that takes a star, follows its evolution from a main sequence all the way almost to the collapse. And there's another code, Geneva code. And we don't know how so you start the star with either no rotation or rotation. So in these models, we started stars with rotation of about 200-300 kilometers per second. That's about 40% breakup velocity. And we followed, with Geneva code, we followed internal rotation and internal angular momentum transport to the surface. And when we impose the stellar winds, and we let the angular momentum to be lost from the star with winds, okay? Specific for a given metallicity and given star mass. So when the star collapses to a black hole, when you go through all the burning of elements, like when you go to iron, and when you collapse, we know at the time of a collapse how much angular momentum we have in that collapsing core. So we can collapse that, and we actually assume the conservation of angular momentum. We don't eject any angular momentum. And we find this is the data from those models, those points. So each point, it's an evolutionary model of a given star mass. Star mass are between 20 and 120 solar masses. And this shows a carbon-oxygen core mass at the end of evolution. Carbon-oxygen mass at the end of evolution is pretty much a proxy for a black hole mass. So you can think is the given star has formed a black hole of about that mass. So from about 10 to about 50, okay? So, and the stars are of different metallicity. So there is one basic trend. Those low mass black holes form with high spins, and high mass black holes form with low spins, okay? Why is that? Low mass black holes come from a lower mass stars, and those lower mass stars do not lose much of mass with wind. So even if you transport angular momentum towards the surface, you don't lose all of the angular momentum. So when you collapse, you have some angular momentum left in the core, and you form a highly spinning black holes. Okay, but this is for lower mass black holes, 10 and 20. But Ligo do see some of them. Okay, for high mass stars, winds are very excessive. They, like I told you, they remove a lot of mass, like 80% of mass. Okay, so therefore, if you transport somehow angular momentum, even not very effectively, you lose most of the angular momentum. You slow down the core almost to zero. When you collapse to a black hole, you have a low spin parameter. So this is a black hole spin parameter, J over mass of a black hole squared. Two stars are spins aligned, and I'm assuming that spins will stay in a line even if I give kicks. So I will show you what will be the effect of adding the full kicks. Mm-hmm. No, no. Like I said, in dynamics you don't expect them to be aligned. In dynamics you expect those misalignment angles to be isotropic or close to isotropic. Yes, I didn't. Oh, so you want to catch two stars, but then why would you catch them like this? You would also catch them like this. Yes, and people do include that. It's a very small fraction of. I don't believe it's even close to 1% because people don't even mention those in tables, but they do include those interactions. But mostly, what people think, you either so there are two major modes. You either form black hole in one type of systems and you eject it from it was binary or triple or something, you eject it, and then you catch it by a different another binary. Then you still keep ejecting them and exchanging. That's why you see here like 40 interactions. I can show you the detail of the pictures later. Or you actually have so you keep exchanging them over and over again. So really you don't expect anything like this. It's just isotropic or semi-isotropic. But then stem binaries that are very close or hard initially, and we have them, you will not disrupt them. So they will evolve and they will form it from those two stars, even if they will, but so you will form black holes from original stars. However, you have so many flybys that you can, do all crazy things with spins. They will be still strongly, even if you don't disrupt the binary, you will be strongly interacting with a bunch of stars in a cluster. So that's why you don't expect aligned spins in dynamical evolution. But that channel, I cannot give you the number. I know people do estimate it, and I know who can ask. So if you stop me in a break, we can send a short email, and that guy will give us the number. I don't have that number in my head. But anyway, like I told you, we could explain one case, okay? I can, push things, and I really have to push, fine-tune things to get to the upper limit, well, 90% critical limit, to get it with binary evolution. But, just to be honest with you, let's see if I do entire population of stars, and I produce, I take that entire visible universe, I produce all my double black holes, and I do two models, one with kick, one with no kicks, like here. So my spins are totally aligned, but I will try to, and then my spins will be kind of high, but then kind of maximal effective spins. But then I use a model with really high black hole kicks, and I try to misalign them to bring them to kind of negative values. So that will be my kind of limiting case, okay? Because if I give them even higher kicks, I will disrupt all the double black holes, okay? So I show you two cases, and I will oppose that against LIGO observation, because LIGO estimated the effective spins for all of us for all 6 cases. So here is the data. So here's the data, 6 LIGO double black holes, and pretty much almost all of those effective spins are consistent with 0, very low values. Okay? That model, that black model, is population model from binary evolution channel, shows you distribution of spins when I don't give black hole any kicks. So this is detection weighted probability, pretty much a detection rate. It's a log scale. So pretty much most of my systems sit at high spin, high effective spin. This is not what is observed. And then it drops down very sharply to negative values. But this is, all spins are here aligned. That red model, I give black holes large kicks so I can try to misalign them, so I get more negative kicks. And you see, I do get more negative kicks. But still, it's not consistent with what LIGO is seeing. Okay? So this is totally inconsistent with observations. So you even can say that this channel doesn't work, or you can ask, why do I get the type of distribution? And I get the type of distribution because of that assumption. Because I have allowed a lot of black holes keep large spins. In that model, we have assumed that angular momentum transport is mild. It's not very efficient. So one solution to that would be to take all those black holes, those points, to change the models, change the input physics, and lower those things down. If all my black holes in the models are born with low spins, it would mean that I will collapse those distributions to here. to 0 because the spins are small. So your effective spins are naturally coming out of 0. And if this is true, if those black holes are coming from binary evolution channel, then we'll have to do that. And it tells you something really important. It tells you how stars work inside massive stars. And this is, we don't have any other means actually to probe that. Electromagnetic observations that you could do to probe inner rotation of stars, massive stars, it's astroseismology. You measure the pulsations of star. You can look deep into the star. But it works only for stars below 10 solar masses. Above 10, so for those stars that make black holes, 50, 100, or even 30, you cannot do astroseismology because atmospheres are fuzzy. They do all weird things. You don't see one clear atmosphere. You cannot do astroseismology. So if somebody can show that, you know, those black holes are coming from binary evolution channel, it tells you something how inner rotation and angular momentum transport works in those massive stars, and that would be great. And this also tells you a lot of other things. It tells you that if those black hole spins are low, you have to form them with low spins, but you can also not increase those spins, and then it will eliminate bunch of possibilities. Let's say to make black hole spins high, you can start with high initial rotation. If you have high initial rotation, your black, and if you don't transport the angular momentum out efficiently, your black hole spin will be high at the end. So it cannot work. You cannot accrete onto the star a lot. Let's say this point here. Even if you started with low spinning star, so you would hope to make a low spinning black hole, but if you accrete even a few solar masses onto the star, you will spin it up to breakup velocity. So it probably will tell you that either you don't accrete as much onto that star, which we don't know from electromagnetic observations, or if you accrete it and span up that star to critical velocity, angular momentum transport has to be very effective. So that's another message. Then we already know that, but it will be good confirmation. You cannot accrete much onto a black hole to spin it up once it was formed, okay? And finally, there are some groups, and three among others, who claim that in that stage, when you have a black hole and Wolf-Rayet star, just before double black hole formation, you're in such a close orbit that black hole can impose tides on that Wolf-Rayet star and spin it up, almost to breakup velocity. And that would mean that the spin of a black hole will be much higher than what we do predict from our simulations, okay? So if black holes are born with low spins and if they come from the channel, all those possibilities are out. Or otherwise, a different formation channel is in place. But we don't know which channel works right now, so we kind of left in the air right now. We need more observations.
Chris, can you go to the next slide? No, the one sort of after that. Yeah. So the prediction. So if the formation channel is dynamical evolution, where the spins are isotropic, the prediction then would be just flat.
No. Since look, prediction. So isotropic distributions of spins. It's theta 1, theta 2, but you have cosines. So when you take isotropic distribution of those two angles, two cosines, they build a triangle function like this. So the distribution would be here, triangle like this.
Okay, so it's not flat.
It's not flat. It's a triangle. So that seems to be it's consistent. But if you have more observations consistent with 0 and no wings of a triangle, it will eliminate dynamical channel as well. So with more observations already in, well, you know the answer. You know the answer. So that's an issue. Both black holes in dynamical channel and evolutionary channel are born from stars. So the same angular momentum transport should work. So if stars are efficient in removing angular momentum, it will affect both channels. It will mean that spins are in both channels low, and that it will tell you that you cannot tell those channels apart. I mean, I will collapse my curves to here, dynamical will come to here as well. No, I cannot exclude. Correct. Yes, well, but yes, correct. that was what we were saying, that if you have triangle, it would mean if spins are high, and if you don't see wings, then, you know, only then you could exclude, but you would have to measure the spins from somewhere else. So actually, that would be a good point. You see, all those LIGO spins seems to be low. So, but it doesn't have to be so there's other options that magnitude. So of course, if you lower the magnitude, if you make magnitude 0, this is 0. But you can play with cosines. So let's say the magnitudes are high. You can, let's say we are here, binary, two black holes. You can put both of them in a orbital plane. If you put them in orbital plane, I know it seems crazy, that comes to 0. Actually, there is a channel to do that. Triple channel. You have a triple systems with a quasi-Lidov effect. Antonini et al. You can check the papers. Antonini et al. 2017, 2018. He has a way of actually the triary companion putting those two black hole spins right in the plane. It sounds crazy. I don't fully understand that, but there is a channel. Okay. Another option is, imagine you have spins of masses of those black holes for all LIGO events are about the same. About mass ratio close to 1. Imagine that the spins are about the same, because similar stars. So now what you would have to do to get it 0, you just do this. You just flip one of them, like this. I don't know how to do that, but we don't fully understand supernova explosion either. Nobody has a full successful model of supernova explosion. If somehow, you know, when you look at the first supernova happens on a very wide orbit, thousands of solar radii. Second supernova or core collapse, I don't assume any supernova here, but it could be some supernova, happens on a very close orbit. If somehow that supernova doesn't change the stellar spin and second supernova flips it around, maybe, I don't know, I wouldn't put my money on it, but I'm just saying there are other ways of making this 0. But if like you're saying, if those, that's actually my feeling. My feeling is that actually stellar spins are small in a core at the time of core collapse, and when they form black holes, the spins magnitudes are small. That's why this is small. And then you cannot tell the channels apart by spin measurements. But there is an issue, big issue with such a statement. The only 3 measurements of high mass X-ray binaries, we have 3 measurements of spins from actually having a black hole and from an electromagnetic spectrum, from electromagnetic observations, and a companion, high mass companion feeding a black hole by stellar wind. 2 are extragalactic, 1 is galactic Cygnus X1. We have 3 measurements of spins. 1 is measurements of that A. 1 is 0.7, 1 is 0.82, and 1 is 0.98. So all the high mass X-ray binaries that we know with high mass black holes and a high mass companion seem to have almost maximally spinning black holes. What's going on? Nobody knows. I actually evolved those 3 systems forward in time, and they're not massive enough to produce double black holes. They can possibly make a black hole neutron star, but not a double black hole. So maybe there are different populations. Those high mass X-ray binaries are progenitors of not double black holes, but something else, while those double black holes from other systems. But there is something definitely going on here. And one solution is to make that spin low for all LIGO double black holes and learn something about stars, or come up with a different channel. And which answer it's true, I don't know. Okay, I'm gonna stop here. I'm gonna skip. We want to be on time for dinner. If somebody wants to talk about, I'm gonna skip one subject, which is population 3 stars. But this is simple thing. If somebody's interested, please, I'm here for like 10 more days. Just catch me and I will give you the story, okay? By the way, I forgot I have a neutron star to talk about. 5 minutes? Can I take 5? Okay, so sorry, I will spend 5 minutes on the neutron star. This is a doubly puzzling event. Population synthesis and evolutionary predictions, and it's not only mine, other groups as well, do not predict detection at this level of sensitivity. And it's not only rate, it's also the host galaxy. So I know you had talks about this or you heard about this event, so I'm not gonna talk about this to save time, but there's 2 things that I find very surprising. The high rate, so the rate estimated by Ligo based on that one event is 1,500 per gigaparsec cube per year, compared to about 100 for double black holes. Okay, much higher. Of course, big error bars. It's Poisson statistics of 1. Okay, and then the host galaxy was massive elliptical. That's also very puzzling because there's no ongoing star formation rate. So here, the rates that so why I find it surprising here. When you actually calculate the rates of neutron stars, the most we get, when you look at the LIGO volume, it's about 100 megaparsec cubed. The rates, and when you calculate all of the galaxies, spiral, star forming, and ellipticals, all of the galaxies, you get to rates of about 100. So 15 times lower than what LIGO is predicting. And it's consistent across different models. Thomas Tauris, Ilya Mandel, me, other people, we do get about 100. And this comes to the fact that it's rather narrow band of neutron star formation rate range, about 10 to 20 solar masses. A lot of stars die in common envelope, a lot of binaries get disrupted in supernovae. We kind of think we understand those issues. It's hard actually to crank up all those parameters in the favor of neutron star formation to get that high. Martina tried it with about 40 models. She got as high as as 300, 500. So possibly if the rate goes down with future LIGO observations, we can explain something to about 500. Okay, with low rate, but we cannot explain such a high rate. But this is, I'm emphasizing, this is if you take all types of host galaxies within LIGO volume. But let's for a moment, just for fun, play with the fact that this is actually typical for neutron star mergers, ellipticals, and let's actually count all ellipticals within a LIGO volume, within 100 megaparsec cubed. So we've done that, and we estimated the rate from all the possible neutron star formation channels, and we estimated the rate from binary evolution channel, from dynamical channel, nuclear cluster channel, and those are all pretty much major channels that you can do. You cannot do homogeneous evolution, the one Ilya was talking about. You cannot do neutron stars with that channel, but that's another issue. So the LIGO rate within that 100 megaparsec volume, you see that rate is per gigaparsec cubed. So if you take 100 megaparsec cubed, you just it'll be, instead of 1,500, it'll be 1.5. You just reduce that, but by 3 orders of magnitude. So the LIGO rate per year is 1.5 detections in that volume. And here you have evolution of formation of neutron stars in different channels. I'm not going to go into the details, but in each channel we try to crank the parameters up so much that we are already uncomfy about some of the assumptions that we try to make neutron star formation as efficient as we can. Look at the rates, but it's just from ellipticals in that LIGO volume. So from ellipticals, binary channel, 10 to minus 2, 2 orders of magnitude below LIGO estimate. Global clusters, it's 5 times 10 to minus 5. It's just no contribution. Nuclear clusters, 10 to minus 5. We simply don't know how that thing has formed, unless it was a double fluke, both in rate that we have seen it and in host galaxy. We have no, like for black holes we have multiple models. For neutron star we have no model. Thank you, I'm gonna stop here. Yes. Yes, it does. Yes, yes, sure. Can I okay? where the LIGO is, but we're not where the predictions are. So that's why I would say. Yes, yes, no, no. So I'm saying, so exactly. So I agree with you. So I want to play exactly on that rate. I would like that rate to be that high because then we have no way to explain it. We're gonna rewrite textbooks. I would be perfect. So I fully agree with what all you said. I was surprised before I got observations, and now I'm not. I would bet also on the most massive galaxy. We're doing something wrong. There's something fundamental we don't understand. Totally agreed. Totally agreed. Surprisingly. Well, if you guys have any questions, stop me anytime you want, okay?